Okay, I'm going to show you how to do the worksheet on orbital notation. I've already gone over all the rules for filling. On the worksheet, it'll say, and I don't have a copy of the worksheet, and I had problems printing it. It's one of those things that disappeared, but I'm going to replicate it. Okay, draw an orbital notation and electron configuration for pick something out, phosphorus P. Okay, so when I look at P has 15 electrons. Now here's what I like about it. They give you the orbital notation in an upward direction. So they give you your 1s. And then it comes next is your 2s. Then at a little higher level is your 2p. Then a little higher is your 3s. And a little higher is your 3p. Now here's how easy it is to do it when you have this in front of you. Fill 15 electrons. You're going to fill it up like a glass of water, following the rules. 1, 2, that's off-ball principle. They occur at the lowest. So my first one is 1s2. Okay. The second one, 1, 2, fills the 2s. And this is all you have to do on the homework sheet. That's 4 electrons. I need to get to 15. 5, 6, 7, 8, 9, 10. That's 2p6. Right there, that would be the configuration of neon. Okay. Keep going. I have 10 electrons. 11, 12. That would be magnesium, 3s2. 3s2. And then finally 13, 14, and 15. So 3p with just 3 in it. So there's your configuration, the full configuration for phosphorus. Now there is a shorthand way. If you're doing configurations and you do something like radon, you have to go through every single configuration. That's really long. Well, you can use a shorthand called noble gas configuration where you just start with the last noble gas, and that's what I did here. This inner core, this right here is the inner core. Electrons are the noble gas neon. These are called your outer electrons. These are the important ones. These are called your valence electrons. So these are your valence electrons. Now they're the ones involved in bonding. This is inner core. And the reason why we're learning this is so we can get the bonding, okay? And when you get the bonding, if you look at this configuration, and let's draw it out. It was, do it down here. 1s2, 2s2, 1, 2, 3 for the p, 1 for the s, and 3 for the p. 1, 2, 1, 2. I'm drawing it out horizontally. Just violated a rule. 1, 2, and then 1, 2, 3. Now if you look at this, there's 3 open spaces for electrons. So if I look at the valence electrons on phosphorus, I have 2 electrons in the s, and then 1, 2, 3 in the p. That's called the Lewis dot diagram. It shows the 2 electrons for the s and the 3 singles for the P. Well, the fact is phosphorus has room for 3 more electrons. So I could put 1, 2, 3. It now picks up the noble gas configuration of argon. 1, 2, 3. It's stable because it had room for them, but it gets a -3 charge. And that's why phosphorus gets a -3 charge. Oxygen would get a -2 charge. Oxygen has room for 2. Any halogen has room for 1. It's a P5. So the charges come from the configurations, and that's pretty cool. Exceptional configurations. Exceptional configurations tend to be precious metals. And then the exceptional configurations, the reason is that half full orbitals are more stable. The reason they're more stable is there's less repulsion. There's no electrons repelling in a single one. And another reason, this will sound odd, full orbitals are more stable. And both of these are then partially filled orbitals. The reason isn't less repulsion, the reason is more protons. And that means more attraction. When you have a full orbital, you also have more protons, which will have you want to fill up that shell. So here's two that are there are chromium, and right under it, molybdenum. They have exceptional configurations. We think of chromium as being, and I'll do its noble gas configuration. Here's chromium. Last noble gas is argon, Ar. Then after argon, number 18, comes 4s2. Then we drop into the Ds, which is a 3, D, and we'd say 1, 2, 3, 4. So if I look at its orbital notation, five Ds, D is L equals 2, so I'll watch this, +2, +1, 0, -1, -2. These are your 5 D orbitals, meaning there's 5 of them. Okay, 2 here, and then 1, 2, 3, 4. Well, these 2 electrons repel each other, and there's room here for an empty orbital, and it violates the off-ball principle. This electron is more stable to fill that one, and so your actual configuration is 4s1, 3d5. The effect of that is they're all parallel, and it's more magnetic. All these parallel bonds gives that metal more magnetism. And one other thing, when you fill these all up, the ones inside block the one outside from the attractive force of the nucleus. It makes this one right here easily excited. So it, trying to go to AP Chem for a second. They'll look at that energy of excitement and tell you that that goes down, but I'm missing the name for it. They use it to study atoms. Anyway, chromium has this exceptional configuration. Because it's easily excited, it's a better conductor, and it's more lustrous. This electron is more easily excited, so it's simply more shiny. And that's why they put chrome on bumpers. Better conductivity, more lustrous, and more magnetic. We get all those properties for chrome. If I do molybdenum, here number 42, it's got krypton as its last noble gas. And then you get 5s1, and then 4d5. And we see this again. There's one electron in every orbital, so there's less repulsion. Okay? And then it's violating Aufbau's rule because this electron's in excited state technically. Okay? But that's why it's an exception. Molybdenum is used in like a super magnet. Very magnetic. And again, you get a high luster, you get a high conductivity to it. They call that the electron potential. The potential energy it takes to jump it up. It becomes lowered. Okay, now, this is half full instead of full. And these are all half full instead of partially full. So that's two of them. The other exceptional configurations and it affects their properties are copper, silver, and gold. Okay? Here's copper, argon. Same thing. You expect it to have a 4s2, but it has a 4s1. And then the D's are full, 3d10. So in this case, you got half full and full. Well, what's happened, because you got more protons in it, is that this electron really got sucked in to fill that. That's my explanation for that anyway. That you got more proton, more Z effective. Effectively, that 4s1 is now held looser, so it's a better conductor, and it's lustrous. That's why these were always precious metals. Silver, you start with krypton. Instead of 5s2, you get a 5s1, half full, and then you get 4d10. Again, it's like Yukon Cornelius and Rudolph the Red-Nosed Reindeer, silver and gold. The luster made them always valuable, and they're better conductors. If you're going to have high-tech electronics, in your household you might use copper, but in high-tech you might use silver, but in a higher tech, like an F-22 Raptor, you're going to use gold for all your connections, because it's a better conductor. Gold would be xenon. Here's gold, AU, 79. To find the last noble gas, you can just count backwards, or you could go up one level and all the way to the right. Xenon. Okay, gold's a little interesting because you go to xenon, and there's your 6, which goes 6s1. That's the one electron that'll be borrowed. But before you get there, you got to go into the F's. 4f14. Those are all filled in an inner orbital. Then you get done the 14, you go out here to the D, and you get 5d10. Half full, full. And that's what exceptional configurations are about. And if I went through this entire, I can try doing this real quick. Let me go sideways. If I tried to do 118, I can go through all the orbitals. I would start with number 118, 118 electrons equals 1s2, followed by 2s2, followed by 2p6. I'm getting it right off the periodic table. 3s2. And I just follow the numbers. 12 next is 13. That's 3p6. Keep going. I'm at argon. 4s2. I'm at calcium, and now I go into an inner level. 3d10. That's zinc. They're all paired up. Zinc isn't magnetic at all. That's called diamagnetic. When they're all full, diamagnetic is not conductive. When they're half full or it's spinning parallel, that's called paramagnetic, and it would be attracted to a magnetic field. Gallium, back to a 4p6. I'm at krypton now. I go to 5s2. I think I should have started over here. Kind of compress it. 4d10 gets to a 5p6. Now it gets interesting. 5p6 xenon, I go to 6s2. And now I got to go into the inner transitions. 4f14. Now I can continue to 5d10. That would be mercury right there if I stopped. Then where I'm at, 6p6, and then 7s2, and then down to the F's, 5f14, and I think I made it. The last one will be 6d10, and the last one is 7p6, and that would be number 118, which I can't remember the name. It has a name now. If I do 118, if I did all that work, that repeats itself over and over and over again. The patterns in the periodic table. That's why the pattern is in this. You can read the pattern and just go up to it. And that's how you're doing configurations. Easy. If I want to do an 18, well, it would certainly be easier, instead of doing all these, to go up to the last noble gas. Right above it is radon. And so this is my noble gas configuration. Starting with radon, 7s2, okay, and then 5f14, then 6d10, then 7p6. There's my valence electrons, and there are my valence electrons right there. Radon would be everything up there, up to 6p6. And, you know, periodically, every group ends with the same number. P6, 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 P5, P4, P3. These are gaining electrons, metals. S1 doesn't have a lot of a lot of protons, so they lose that S1 to all become a +1. They lose that S2 to all become a +2. The metals, this family, loses all the P1s and the S2s to become a +3. But on the other side of the world, halogens become a -1 because they gain 1. Oxygen becomes a -2. Nitrogen becomes a -3. And I think that's it for quantum theory. Do all your worksheets. I'm going to put a review packet. If you have any more questions, I'll try and put some more packets in. It's not too bad. Really read the book. So go buy the book. Definitely look at your PowerPoint and look at the notes I just gave you. And I am now done 6.